Welcome to the IDSS-Targeted Threat Messaging course, an addendum to the Mesoscale Environment Analysis course. This is the first course unit, answering the question, in the new era, focused on IDSS, when it comes to threat messaging, are watches and warnings alone enough? I'm Pete Wolf, the SOO at the Weather Forecast Office in Jacksonville, Florida. There are different aspects to what we call Impact Decision Support Services, or IDSS, ranging from social media graphics and chat messages, to detailed partner briefings, to on-site deployments for major events like hurricanes. Well, one aspect is something called Targeted Threat Messaging, or TTM, which is the main focus of this course. To understand the value of TTM in operations, let's start by looking at watches and warnings, and the issues associated with them related to promoting correct and timely decisions. We need to understand the problem first before we can focus on a solution. That's the purpose of Unit 1. This module will illustrate the role of watches and warnings in the Weather Service mission and what they may lack when it comes to supporting IDSS messaging. It sets the stage for demonstrating the value of TTM in high-impact operations. A few cases will be provided to demonstrate this. As you know, the key products related to our mission include the watch, representing area with potential for a given hazard, and the warning, representing area where a given hazard is likely or occurring. That's it for our mission. Update products or other messaging are strongly encouraged, but not really required. So we need to assess whether watches and warnings alone are sufficient to support IDSS for our partners. Do they provide the detail and specificity needed to support actionable decisions? Of course, you know the answer, as this course wouldn't exist if the answer was yes, right? Just as review, watches are generally large-scale areas of potential threat, covering a certain period of time, which differs by hazard. For severe convection, watches are generally issued for 6 to 8 hour periods and cover portions of one or more states. For the flood hazard, watches can be issued up to 24 hours in advance and can cover very large areas, including portions of multiple states at times. Finally, for winter storm hazards, watches are issued well in advance, and it's the warnings that are issued up to 24 hours in advance. They can also cover portions of multiple states. How would you answer this question? True or false? Convective and flood watches and winter storm warnings provide timing information on the hazard to support decisions being made in different locations within the watch or warning areas. That is false. A general timing range for the entire watch area may be provided, but not necessarily focus on any specific part of the watch area. Take a look at this example of a fast-moving convective system with damaging winds heading for southwestern West Virginia. Conditions are not favorable for severe storm development ahead of the line, so our focus is on the damaging line itself. Think about how you would answer the question shown here. Given this scenario, with a Boeing line segment producing widespread damaging winds, thus a really high-impact event, one could focus messaging on the southwestern part of the watch area for the next 2 hour period. Thus the answer is A. Of course, one could also message southeastern West Virginia to indicate there is minimal threat for the next 2 to 3 hours or so, with rapidly increasing threat thereafter. In this example, there appears to be a substantially greater threat for damage in the southwestern half of the watch area compared to the northeastern half, which one could message. Now, there will be times when you have hazard development across the watch area where you cannot necessarily downscale messaging to a particular portion of the watch, as shown by these examples. In such cases, downscaled messaging may be limited to hazard initiation, perhaps prior to watch issuance and during the warning periods. Here is a flash flood watch example for an approaching tropical cyclone. We might be confident of little potential for flooding for a certain period of time, such as the northeastern half of the watch area in this example. Our focus during the next 6 to 12 hours may in fact be focused on the southwestern portion of the watch. Due to the slow movement of the system, we could message little flood potential for the next several hours in the watch area, rather than just limiting our message to the flood watch text that indicates potential across the entire watch area during the entire watch period. Let's try this case scenario with Hurricane Sally moving northeast at 20 miles per hour. Note the points A through D on this image. For which point could one focus messaging on the setup of training convective bands that could promote a flash flood threat over the next few hours? The answer is D. We often see training convective bands on one side of the circulation, with the band set up parallel to the system motion vector. Now, one could also select B, though I'm assuming the heavy precipitation is spreading northward, not just training from east to west around the circulation. For which point could one focus messaging on the continuation of heavy rainfall and worsening flood conditions over the next few hours? That would be point B. There's a broad area of heavy rain from south central Alabama eastward across southwestern Georgia. At point B, the heavy rain will likely continue for a while. Point D, of course, would not necessarily be incorrect. For which point could one focus messaging on the end of the heavy rain threat during the next 1 to 2 hours? That likely would be point C. The heavy rain there should taper off after the storm center passes, based on this image. So in this scenario, while we likely have flash flood watches over all of Alabama, Georgia, and the Florida Panhandle, we can distinguish areas of greater or lesser threat and threat timing differences. For winter storms, warning products also tend to provide more generic threat information for the entire warning area. But we could have the ability to downscale our messaging to focus on the location and timing of precipitation type changeovers, or of heavy snow accumulations, or the timing of the start or end of impacts. Note this 19Z radar image showing heavy snow bands that are slowly progressing eastward. Consider what could be messaged for the Dallas-Fort Worth area when it comes to threats for the late day rush hour. How would you answer this question regarding the Dallas-Fort Worth area? You should get a sense that conditions will quickly worsen as heavy snow moves into the area from the west. That detail for Sunday afternoon is not provided in the warning text message shown on the left, which describes the general threat right through late Monday. Here's another winter weather example, focused on the Chicago area. During the night, we have very light snow occurring across northern Illinois. As we approach dawn, areas of heavier snow spread northeastward across north central Illinois toward the Chicago area. So how would you answer this question? How will conditions change in the Chicago area over the next few hours? It should be pretty clear that conditions will be worsening in Chicago as heavy snow moves in. Can we, and should we, message this to partners, or is the warning message enough? Let's turn to short fuse warnings, thus warnings for severe storms or floods. With WarnGen and Hazard Services, the text products are automatically formatted based on the polygons we draw and menu items selected. Unfortunately, these technologies are not as good in communicating with precision compared to humans, and can frequently generate errors or confusing things in their output. How would you answer this question, in general for all warnings, not specific to the one shown? In general, the correct answer is all of the above. Errors or confusion can occur in any of these sections. Let's start with the top section, describing areas within the warning polygon. What errors can exist in this section? Well, the description can be wrong and confusing, especially if you have unusually shaped counties. It can include a county you don't wish to warn by accidentally clipping a tiny part of it in the polygon. It's important to note that people may not even know what portion of the county they are located. Here's an interesting tornado warning example. Think for a moment how you would describe the portions of counties covered by this polygon. I would go with northern or north central Duval County and perhaps extreme southern Nassau County. The latter one is a little tricky. However, WarnGen comes up with something very different and wrong. It has central Nassau County and northeastern Duval County, which are not really the portions within the polygon. Isn't that odd? Getting this correct can require manual adjustment at times, unfortunately. How about this section of the warning product? What errors can exist? You can have an incorrect location of a hazard. WarnGen treats a hazard as a point and not necessarily as a larger area. WarnGen does not deal well with multiple hazards within the warned area. Here's an example. A tornado warning focused on a circulation northeast of Dakota City, as indicated by the arrows. However, you'll note another circulation and reflectivity appendage further west, and even a third circulation merging in from the north. These are not mentioned in the text product, but it can make a confusing result. In this example, the storm is indicated to be 7 miles northeast of Dakota City, moving northeast away from Dakota City, and yet Dakota City is in the list of locations impacted, as it's in the polygon, which includes the western circulation. The western circulation, however, is not mentioned. Here's another example. The text product indicates the storm is 5 miles west of the town of Volland, indicated on the images by the black X. As you can see, however, the storm is actually north of the X, and the storm isn't a single point, but rather a large area. Based on the radar image of the southward moving storm, do you think the highlighted town of Volland is in its path? Probably, and yet you'll note that Volland is not in the locations impacted section, possibly due to the small size of Volland. How about the locations impacted section? It can be odd how WarnGen determines the towns that it will include in this section. We can have incorrect locations, missing towns due to an incomplete cities listing in the AWIPS. Potentially confusing information here. Here are the towns mentioned in LSRs as being struck by the tornado for this example. The only town in this list, and the list in the warning text product, is Union Grove. So did people in the other towns struck know they were in danger? Here's an interesting comparison of the warning text product and its associated Twitter graphic. The black ovals highlight towns mentioned in the text product, but not highlighted on the Twitter graphic, while the blue ovals highlight towns shown on the Twitter graphic that are not mentioned in the text product. So which is correct? Or are they both partially correct? In this example, the text product has a path cast. If it did not, as in most cases, how could someone tell from either product what area is in imminent danger during the next 10-minute period? It's nearly impossible to tell without additional information, such as a radar animation, for example, or downscaled threat messaging. Here's another confusing example. The warning text product indicates a storm over Ocean Way. The map to the right shows the location of the storm core, which is drifting northeastward at just 5 miles per hour. The storm is not over Ocean Way, nor, given its northeastward motion, is it going to be over Ocean Way in 22 minutes as given in the pathcast. It's actually headed toward a community called Jacksonville North Estates, east of the airport, but that is not in the text product. Finally, it indicates Jacksonville in the pathcast, but is it referring to downtown, which is in the other direction? This text product needs a lot of work to not provide confusing or inaccurate information. It illustrates that the human can do considerably better. What about the preparedness section? What errors could possibly exist here? Likely no errors, since this is pre-designed information. The question is whether or not, for a given situation, it is actually the information the meteorologist wants to convey. Would he or she convey this if manually typing this product? In this tornado warning example, it indicates take cover now for the entire warning area. But does the meteorologist really want to communicate that for the entire polygon? In this example, he or she may really want this advice to focus on the area highlighted by the blue oval, in the immediate path of the mesocyclone, right? The human can do considerably better. A key point of this module is that humans still outperform technology when it comes to messaging. Humans can communicate better downscaled information to support threat confirmation and personalization steps that can lead to better actionable decisions. Control of the message is key. There are other issues with short-fuse warnings that I will briefly discuss. The first deals with false alarms. The primary statistic used to measure false alarms is false alarm rate, or FAR. It is simply calculated as the ratio of unverified warnings to total warnings issued. For tornado warnings, this statistic has been pretty steady, near 0.7 for many years. Thus, over 2/3 of tornado warnings issued do not verify with a tornado report. But is this similar to what individuals observe in their local areas? Do they see tornadoes during 1/3 of the tornado warnings they are under? The main problem with this computation is that there is no penalty for warning size. In other words, if every tornado warning were drawn the size of the continental U.S., false alarm rate would not increase. It actually could decrease slightly by catching a few events that occur just outside our polygons. That does not make sense, does it? To assess location-based FAR, one has to incorporate warning area. To assess this, I completed a simple study using reported tornadoes and warnings issued over a 5-year period from the start of 2016 to the start of 2021. Based on the average warning size of 294 square miles and 12,000 warnings issued, you get a total warning area around 3.5 million square miles. To put that large number into perspective, The area of the continental United States is around 3.1 million square miles, so we're talking about 1 1/8 conuses of area warned during this 5-year period. That's pretty large. In comparison, what area was struck by the nearly 7,000 tornadoes reported during this period? Most tornadoes are small, maybe 100 yards wide and a few miles long. I also wanted to include a buffer area, where one is close to being struck. So I came up with a total of about 3 square miles. That's about a half a mile wide and 6 miles long, to include the buffer. Turns out, whether you use 3 or 6 or even 9 square miles, it won't change the result that much. With 3 square miles, I get a total of area struck or close to being struck of about 20,000 square miles, which is roughly the size of half of the state of Ohio. I then generated area-based FAR by computing the ratio of warning area not struck or close to being struck divided by total warning area, and came up with 0.994, not 0.70. Is the problem that polygons are drawn too large relative to the hazard? Maybe. I tried reducing polygon size by 2/3 to just 100 square miles. That reduced 2 million square miles of false alarm area, so you'd think that would substantially reduce area-based FAR. It does not, as FAR drops only to 0.97. Very disappointing. In fact, to get area-based FAR close to 0.7 or 0.8, the polygon has to be reduced to just 10 square miles in area, so 2 miles by 5 miles. That's hard to do with warn gen or hazard services, but that's not the case with downscaled threat messaging. Given this Twitter image of a tornado warning, where is the tornado hazard? And where is it going? Can you tell from this image? It's okay to have a larger polygon, but we need another form of messaging to downscale this and communicate specifically the where and the when. One other issue to discuss is lead time. This is an important slide as we focus on how lead time is related to IDSS. We usually focus on lead time that's needed to take protective shelter, but there are more decisions made than just that, covering a range of lead time periods. Only some examples are shown here. It's not anywhere near a complete list. Essentially, the greater the lead time you provide, the greater the range of decisions your effort can support. If you provide just 5-minute lead time, you primarily support just decisions to take immediate protective action. Someone in a mobile home ahead of an approaching tornado might have little choice than to ride it out there, which is not what we want them to do if there is not sufficient shelter there. What if you provide a 20-minute lead time? Well, then you support a greater range of decisions, including having the mobile home resident find sturdier shelter, perhaps a school, church, or other substantial building. What about a 45-minute lead time? Then you support other types of decisions. You might give someone at work or a store time to finish what they're doing, then drive home to shelter with family, for example. If you have a violent tornado heading towards a major interstate, you might be able to give law enforcement time to shut down part of the interstate to prevent motorists from driving into the tornado as it crosses the interstate, but that takes time to implement. So there is a direct relationship between the lead time you provide and the decisions the information can support. Here's the Twitter warning example again. Can you tell who needs to take cover now and who needs to monitor the hazard over the next 30 minutes to see if they'll need to take cover then? No, we need something else to provide this. Question: are warnings the only means of providing lead time? Or could it come from other messaging, perhaps through partners like TV meteorologists? So are you understanding the issues associated with watches and warnings that can negatively impact threat confirmation and personalization that's needed to support correct, actionable decisions, be it to take cover when in danger or to not take cover when not in danger? Let's go through a few exercises to further illustrate these issues, which dictate the need for targeted threat messaging. Take a look at this warning text product and associated Twitter image. The black ovals are towns in the text product not on the Twitter image, while the blue ovals are the opposite. Pretty striking how different these can sometimes be, particularly when you have a large number of towns within the warning area. You may not see this if you just have 2 or 3 towns within the polygon. So can you tell from either image what towns need to take immediate protective action, as opposed to action 30 minutes from now? Actually, you need additional information. The text product suggests the hazard is along a line from Dunkirk to Golden Beach, shown here on the Twitter image. Thus, the imminent threat area would be the area shown by the white dashed polygon, right? However, the radar image shows a Boeing line segment west of these locations, with the imminent threat area extending west to include towns like Aquasco, which interestingly is not listed in the text product. The town of Brandywine on the western border of the warning is listed in both products, yet it is likely behind the severe wind hazard, although heavy rain and gusty winds may still be ongoing there. If you look just at the radar image, can you tell where Dunkirk and Golden Beach are located? Not without having the towns overlaid on the image, right? It is challenging for someone to know if they need to take protective action now solely based on these products. Based on a radar animation overlaid on a map of communities, could you focus on who is in immediate danger at any given moment of time? Let's try another warning example. Here we have the December 10th, 2021 tornado outbreak event, and we're focused on a long-track tornadic supercell moving northeast toward the southeastern tip of Missouri near the town of Hornersville. We see rather large polygons relative to the area of threat. The motion vector is shown by the white arrow, which is expected to continue as the storm has already deviated slightly to the right of a large mean wind vector. It has moved in this manner for some time. Based on this, what communities appear to be in the path of the mesocyclone, yet are not mentioned in the warning text product? If you look closely along its northeasterly path, highlighted by the yellow dashed polygon, you'll find two towns, Rives and Gobbler, that are not mentioned. It may be these are very small towns. Try this question. What towns given in the warning pathcast do not appear to be in the path of the northeastward moving mesocyclone, and thus not in immediate danger? The highlighted towns here are in the pathcast, but appear to be located well southeast of the expected mesocyclone track. This assumes no further deviation of the storm motion vector, a valid assumption as we already have a strong, deep mesocyclone. On this slide, you see 4 different colored polygons, including the actual warning polygon in magenta. Given the estimated 15-minute motion vector shown as the white arrow, which of the polygons do you think accurately reflects the area where immediate protective action is needed? The answer should be the blue polygon that's in the immediate path of the hazard. This represents the area where immediate protective action is needed. This, however, is not reflected in the warning text product, nor on the Twitter image. Now, which polygon represents area that is not in immediate danger, but offers 30 to 45 minutes lead time to support longer range decisions ahead of immediate protective action? The red polygon would be the correct answer. Here we can support somewhat different decisions to be made compared to areas in the immediate path of the hazard. Let's try a convective watch exercise. Here we have a narrow squall line in a low-cape, high-shear environment. There is little potential for severe storms to develop ahead of the line due to lack of downstream instability. The main show will be the strong winds with the convective line passage. We have a tornado watch shown in red for the next 6 hours. Which polygon that's shown do you think best represents where you would highlight potential for a likely severe storm threat during the next 2-hour period? The black arrow indicates roughly the expected 1-hour motion for the line of storms. The green polygon best highlights the threat area for the next 2-hour period. There is little threat further downstream until later in the watch period. Now, within which polygon would you highlight minimal severe threat during the next 3-hour period, with the threat quickly increasing thereafter? In this case, the yellow polygon might be the best area for such a message, if the environment in this area is expected to maintain storm line intensity. Messaging delayed threat in the most downstream part of the watch area is not indicated in the watch text product. So in summary, watches are the key product of the National Weather Service mission during high-impact events for indicating hazard potential over a given period of time. Warnings are the key Weather Service product during high-impact events for indicating likely, imminent, or ongoing hazards. This module illustrated opportunities within watch and warning periods to downscale messaging in a manner that can support actionable decisions, which is the focus for the rest of the course. Watches and warnings alert for potential or ongoing hazards, whereas TTM focuses on the specifics, the where and the when, to support threat confirmation and personalization that can promote actionable decisions. Thank you for completing this module. Hopefully you have a good sense of the potential value that TTM offers by making up for the issues associated with warnings alone. TTM will be the focus of the next module, Unit 2.